So thanks a lot again for Radu and Yura for thank you very much. So thanks again for the invitation. Words cannot express how happy I am being here. And as Yura alluded to, so a large part of my research is actually based on the man Irving Schrödinger himself. So it's kind of a cherry on top of a cake. So as talking about this result here, I feel like I met my academic grandpa for the first time. Okay. So let's begin by explaining what this weird title is, how to optimize the Schrödinger bridge, and why do we care about it. Okay, so my background is in machine learning, and a while ago, me and my collaborators, so we started approaching this problem. So what you're looking here is a data set of cancer cells of some patient, but expressed on different days, okay? So on day 0 is the red dots, on day 1 is the yellow dots, so on and so forth. So given this data set, what we wanted to understand was to recover the evolution of the cancer cells. So in other words, how did those red dots evolve into those yellow dots? And the mathematical way of formulating the question is to say, I give you a fixed distribution, mu, representing the starting and pre-go distribution on day 0. And what I want is a full stochastic process such that whenever I start from the starting day, you should end up at the distribution on day 1, which I denoted by mu here. Okay, so this is the mathematical question that we want to solve. And so how can you possibly go about this problem? So here's a very simple and very elegant idea. So let's consider the space of all probability distributions. So on this thing here, the 2 given distributions would be just 2 points, mu and nu. Okay, and our goal is simply to find a curve that somehow connects the 2 points. Okay, so how do we do this? Now here's a very simple idea. So to start with, what I can do is I can construct something very naive. I don't know, starting distribution plus Brownian motion, whatever. Something extremely naive. Okay? Now the problem with that is, of course, even if I start from the fixed distribution, it's gonna carry me to a point that's maybe very far away from my target. But this is not a big issue by itself, because what you can further do is you say, I can do some sort of gradient search by bringing this endpoint closer to my target measure by doing some sort of a gradient descent on the discrepancy measure between the 2 points. And given this search direction, I can also somehow generalize this to the whole curve, and then I can do this recursively so that eventually this method might converge to the desirable stochastic process. And the word Schrödinger bridge in the title simply refers to the case where when you compute this discrepancy measure, is given in a KL divergence. So it's some sort of one of the most natural candidates, okay? So this is the optimization problem that we care about. And as an optimizationist, I'm pretty sure at this point, our instinct would be just run some sort of gradient search algorithm. And just for the purpose of illustration, so in this talk, I'm just gonna focus on the continuous divergence of the gradient flow, even though everything I say can be generalized to the discrete time setting as well. But anyway, whatever algorithm you want, okay. So whatever algorithm you use, the first question you want to ask is, does my algorithm converge to the optimal point or not, right? So it seems like a very basic question, so nothing can be more naive. And given the fact that Schrödinger bridge is, it achieves the state of the art in many important applications, so it might come as a surprise to you that for a long time, for many years, the standard training algorithms for Schrödinger bridge, they not only don't converge, but they actually provably diverge, okay? And the first ever convergent algorithm was proposed only around half a year ago by myself and my colleagues. And the algorithm looks like this, okay? So it seems very complicated because it is complicated. So if you look at this slide and you're probably wondering, okay, I don't know anything about the stochastic processes, the Schrödinger bridge, so why do I care about this talk? And the answer to that question is, so the goal of this talk today was precisely to convince you that actually there's a lot of things that you can do to this problem that you thought. And in fact, the major goal of this talk is to convince you that by the end of the talk, you're gonna somehow be like, this is some part of a trivial algorithm. So every one of us can come up with at least a basic idea of how to come up with an algorithm like this. So that's basically what I want to do today. Okay, so now for the moment, forget about this complicated math. Let's go back to the optimization algorithm, optimization problem that we care about, the Schrödinger bridge. and we want some convergent algorithm. Okay. So now the first thing you can notice is that, how do I use the pointer? Okay, sorry, yes. Okay, so the first thing that you can notice is that in Schrödinger Bridge, it's an optimization problem over some stochastic processes, so a bunch of probability measures. So this thing should be highly reminiscent of a standard optimization problem or optimization algorithm called the entropic mirror descent, which is optimization algorithm on the simplest system. So it turns out that the algorithm, the complicated algorithm that I showed you in the previous slide, was nothing but the familiar entropic mirror descent, but with some important twist. Okay, so it's something that we're all very familiar with, actually. And the rest of the talk would basically just to be explaining what those important twists are and why are they useful. Okay, good. So this is the structure of the general talk. Now, before I explain to you what those important twists are, I need to start with a problem that's seemingly unrelated, but just please bear with me. It's gonna serve the foundation for all of our discussions to follow. So the result is the thing that I want to talk about is as follows. So for this, at this moment, forget about stochastic processes, Schrödinger Bridge. Let's go back to something completely elementary. Finite dimensional optimization, unconstrained. Nothing can be simpler. Okay? So for this problem, one of the most elementary or fundamental algorithm is the so-called mirror descent, or in continuous time, called the mirror flow. So what you do is that you construct something that's called a dual variable, and you perform gradient descent or gradient flow in the dual variable. And whenever you want to recover the primal variable, you apply the gradient to the convex conjugate of some convex function. Okay, so so far this is completely standard material. There's a well-known result about this particular algorithm, the mirror flow, which is if you consider dynamics in the primal variable, so the time derivative of the primal variable, then it's gonna evaluate to this simple expression here called the natural gradient dynamics. The name doesn't matter. But what is going to be important for us is how you prove this result. And this result is actually a very simple proof that you can give to the graduate student as exercises. So what you do is you start with a standard result in convex duality that says the gradient of a convex function and the gradient of its conjugate, these should be inverse mapping. So if you apply this expression twice, you recover the original variable. Now, if you differentiate this expression once again, you can see that the second order derivatives of the conjugate of convex function, they are related by the simple formula here. Okay. So now we're ready to prove the result. It's very simple. We want to talk about the time derivative of the primal. Okay. So time derivative of the primal. By definition, I differentiate this guy in time. I get the second order in the conjugate applied to the time derivative of the dual variable, which is just the gradient flow by definition of the mirror flow. And also I can replace the dual variable by the gradient of the primal, and this is just by the first property here. And now the proof is concluded by invoking the second equality. Okay, so far so good, completely standard. But from now, things are going to be changing quite a bit and getting more interesting. Because one thing that is very important to notice in this proof is that it only works for unconstrained case. So what happens when you put constraint? And that's essentially what we're going to investigate. Okay, so for instance, let's consider one of the most important constraints in optimization or machine learning, which is the simplest constraint. Okay, so I want to consider a minimization problem, but subject to the simplest constraint. And on this constraint, there's a standard convex function, just the entropy. And here I also recorded the definition of the convex conjugate. Okay, so the first thing to notice in this example is that the first thing to notice in this example is that the gradient of the entropy, your convex function, and the gradient of the conjugate, so they stop being inverse mappings to each other. So unlike the previous slide, if you apply this expression, you're not gonna recover the variable itself, but it's only gonna recover the variable up to some term, okay? Now you can differentiate this equality again, and what you see is, again, the second order derivatives of the conjugate and the function itself, they start being like with this simple relationship that you saw in the previous slide, but again, there's one more correction term here. Okay? So this seems to be contradicting, what we learn in basic convex analysis, but actually, of course, there's nothing wrong. So what's really happening is that when I'm defining the convex conjugate here, I'm not taking the convex conjugate of the entropy. I'm taking the convex conjugate of the entropy plus the simplex, right? So the standard convex analysis tells you that if you evaluate the gradient of the entropy at its dual, then you're gonna recover itself, but up to a term that depends on the normal cone of the simplex, which is exactly what this extra term is about. Okay? So that's what the standard convex analysis tells you. Now, what's gonna be important in this talk is that we're gonna go beyond the setting of standard convex analysis, because standard convex analysis tells you that there's gonna be one term that belongs to the normal cone of the simplex. But what we're gonna do is we're gonna really look at the case of entropy and simplex constraint. So here we have this specific term. So it's not just any term. Okay, so we can solve everything in a closed form, and somehow this is going to be important for us. And in particular, so if you try to minimize a function f, but subject to the simplex using the mirror flow again, and you redo the computation that I showed you in the past slide, you'll see that the derivative of the primal variable now has a different form. So first, you have this prefactor that is exactly the same as the unconstrained case. But now, it also adds up, there's also an additional correction term here. There's one more term. Now, if you look at this expression, you should get highly suspicious because, without constraint, I don't have this correction term. With simplex constraint, which has the interpretation of probability, I have expectation here. So this guy is highly structural. So a natural conjecture is to say, okay, maybe there is something much more general I can say about how when I incorporate constraint, maybe this correction term will change in a tractable way. Okay? And indeed, there are many different ways you can generalize this result that I show you. So the way we took was to simply say that simplex constraint is a very special case of the linear constraint. It's just the sum of the all vector has to be 1 or some constant. Okay. So the gradient is a 4-dimensional vector. This expectation is the inner product of the pi with the gradient, which is Okay. Okay, so we want to generalize this result, and it turns out that so for the case of entropy, if you use entropy as your convex function, and if you do constraint optimization where your constraint is linear, which includes the simplex as a special case, and if you run the mirror flow to minimize the function f, but importantly, you incorporate the constraint into your convex conjugate, okay? So suppose you run this algorithm to optimize function f, then if you look at the time derivative of the primal variable, it's gonna come out in this very specific form. So there's, and again, so here, the time derivative is just the usual term that appears also in the unconstrained world. But now you have an extra correction term. And this result is gonna serve kind of as the foundation of all the results to follow. So basically, the rest of the talk is to make a clever use of how to use this formula in a smart way. But before doing that, so I want to explain to you what this term really means, just for you to get a better sense of what this correction term can be interpreted as. Okay, good. So, sorry? It's exactly that, but it's not exactly that, but it's very close to that indeed. Okay, yeah. So yeah, indeed. So it is true. What you're saying is true. Okay. Yeah. Okay. So I believe that the best way of and we're not gonna use that result, by the way. So that's not the main point of the paper. So the main point of the paper is actually the next slide. So we're gonna take a very specific linear constraint here, and we're gonna see what this extra term evaluates out to get a better sense of what the term means. Okay, so for the specific example that I want to consider, so first of all, I want to fix the dimension to be 4. Okay, so this is a specific dimension. And as usual, I'm gonna use the entropic mirror descent. So I choose the function to be entropy, and then I wanna perform constraint optimization by incorporating the constraint into my conjugate. But in this case, I'm gonna take this particular matrix A here. So this is a specific matrix A. And if you look at what this matrix is doing, it's just the first row of the matrix is just saying the sum of the variable pi has to be 1. So the first row just corresponds to the simplex constraint. And the second row says the sum of the two elements has to be some number, which I called mu1 here. And then the sum of the remaining two should be mu2. Okay? So this is a specific example. Now what's going to happen in this example is if you consider the mirror flow and you take this example, plug in the formula that I showed you in the last slide, what's going to come out is, again, you have the usual unconstrained term, but then you have an additional weird expression that I show you here that corresponds to the correction, which seems a little bit complicated. However, just let me perform a small trick to help you see what's really going on here. So first, I have pi. I said pi is a 4-dimensional vector, right? So I said it's parameterized by 4 numbers, which I called pi1, pi2, pi3, pi4 here. But instead of calling them pi1, pi2, pi3, pi4, of course I can call them pi11, pi12, pi21, pi22, right? With a lot of generality. And I can do the same thing for this gradient vector. Okay? And furthermore, because in the constraint, this is the mu1, mu2, they're just 2 arbitrary numbers, I can equivalently parameterize my variable as mu1 times something that I call pi1 given 1, and mu1 times pi2 given 1, and so on and so forth. Okay, so far I've done nothing, everything is just reparameterization. However, if you take this kind of special parameterization and you plug that into the expression here, you see something very nice coming out, because this thing bears the very clear interpretation of conditional expectation. So for instance, in the parentheses here, you fix the first index of the gradient, and you take the average over the second index, where the average is taken with respect to the distribution pi, but with a fixed first element, okay? So simply put, so this is the 4-dimensional differential equation, but if you evaluate it at the ij coordinate, so 1, 1, 1, 2, any one of them, then it's gonna come out like the usual unconstrained term, and just minus the conditional expectation. And this conditional expectation is what you alluded to. It's an L2 projection. Okay. Now, why is this the case? This is obviously a very structured dynamics, right? So what is going on? So of course, this is not a coincidence. So this thing comes out from the specific A that I chose. And I guess by this point, you already figured out what I did. So it turns out that this A and B denotes a very special type of linear constraint. It denotes what's called the marginal constraint. So the idea is that I have a 4-dimensional probability vector. So I have a distribution over 4 elements, but I can also equivalently think of it as a joint distribution over two-dimensional elements, right? So instead of saying 1 by 4, I say it's 2 by 2. Okay? And in that case, when you apply A to this joint distribution, then what this constraint is exactly doing is I just fix one of the marginals to be a fixed thing, which I call the mu vector. It doesn't need to be a probability distribution, by the way, but it's just fixing the marginal. Okay. And you can generalize this to arbitrary dimensions. So say you have a simplex with a special dimension k squared, where k is a positive integer. And again, you have the marginal constraint, which is a special case of linear constraint. And then you consider the entropic mirror flow. Then the result that you saw in the last slide is gonna generalize. So if you evaluate, so if you consider the dynamics in the primal variable, it goes with the usual unconstrained term, but minus the conditional expectation. Okay? Okay, good. So if you think so far it's trivial, I'm very happy because this is all you need to know to optimize Schrödinger bridge. Great. Okay, so with this in hand, let's come back to the Schrödinger bridge problem. So it turns out that if you look at the Schrödinger bridge problem, it's actually nothing but a special case of the problems that we just discussed, because all you need to do is to find the proper generalization of our finite dimensional setting to the infinite dimensional setting. So for instance, before we say you have a simplex of a dimension k, it means that you have k numbers, they have to sum up to 1. Okay, that's a k-dimensional probability vector. But now we have continuous probability measures, which simply means that it's a simplex over some continuous space, for instance, Rd. So for each point on Rd, you have a number, and this number has to sum up to 1. So this is what you mean by a probability distribution. And also, before we said if you have dimension k squared, then we can see that as a joint distribution over k by k vectors. But there's nothing to stop you from going from just joint distribution of 2 things to joint distribution of continuously many things. So given any number between 0 and 1, there is going to be a probability distributions, and all of these are going to be related somehow. And that is precisely what it means by a joint distribution. So in other words, when I say P is a stochastic process, it simply means that it's the simplex over Rd and the joint distribution over this index which I call 0, 1 here. And again, you have the marginal constraint. So yeah, so you just need to do this identification, and the rest is just definition tracing. So apply everything that you learned in the talk. So naturally, you would expect that, okay, so now I have an optimization problem with this marginal constraint. So I can apply the entropic mirror flow that I mentioned before, and specifically with this marginal constraint being taken into account by the conjugate, okay? And the only thing you need to be careful about is that instead of a gradient, you need to replace that with infinite dimensional analog called the first variation. But anyway, conceptually, it's exactly the same. Okay, so given our discussion so far, I think it's also pretty straightforward to anticipate that if you look at the derivative of the time of the primal variable, which is the stochastic process here, you're gonna get some global terms and also a conditional expectation term. Okay. Okay, so now I guess we have a pretty, this algorithm, there's nothing mysterious about this algorithm, right? Okay, if that is the case, then if you discretize this algorithm in the most naive possible sense, and if you've done the due diligence to do all the definition tracing, what comes out is precisely this math that I show you in the beginning of the slide. So this algorithm is nothing but the most naive discretization of the entropic mirror descent, okay? And in particular, so here, down here, you see there's this complicated function, which I call V here, that looks like the expectation of something that depends only on x, the input, plus some Brownian motion. So it's a simple expectation. And the right way of interpreting this expectation is this guy is saying, I need to take expectation of a Brownian motion conditioned to start at the point x. So this is a conditional expectation in disguise, and this is precisely what came out in the expression here. Okay. This is exactly a stochastic control problem. Yeah. So Schrödinger bridge is a stochastic optimal control problem. Yeah. Okay. So yeah. Okay. So the last word I want to say is that the reason why I spend so much time on saying that there's a connection between this conditional expectation and whatever. This is for implementation issues. So in order to, it's not difficult to derive the algorithm, it's difficult to implement the algorithm. So in order to implement the algorithm, this formula is really the key here. Okay, so to compute a V and make the whole algorithm implementable, you heavily rely on the fact that there's a conditional expectation. Okay, so this more or less concludes what I want to tell you, for large parts, and just for the final parts, I just want to quickly mention that you can also use this mirror descent framework to do a lot of things for Schrödinger bridges, not only just motivating algorithm. For instance, if you want to conduct the convergence analysis, then here is entirely trivial because it's the analysis of mirror descent or mirror flows, so everything's completely standard. There's zero novelty here. Which I think is a good thing, right? So you have a complicated algorithm that looks like this, whose convergence proof is more or less trivial. So for me, that's a positive sign. Okay. And also, I want to just quickly mention, as a side note, it's not really related to the topic of the talk. So if you consider this continuous time dynamics, and if you discretize it using a very specific step size 1, now this guy turns out to be equivalent to an algorithm called the Sinkhorn, which is an important algorithm in optimal transport or matrix scaling or related fields. You also saw this algorithm in previous talks. So this observation might be of independent interest to some of you. Okay, so finally, since we know so many things about the mirror descent or entropic mirror descent, so there's a lot of other things that we can actually do with the framework to solve the Schrödinger Bridge problem. For instance, you can consider the accelerated version, the variance reduced version, so on and so forth. Okay. Okay, good. So that concludes everything that I want to tell you about today, and just have a quick, brief conclusion. So we started with the problem of Schrödinger Bridge, and we showed that this problem can be optimized using a framework that's familiar to all of us, the entropic mirror descent. But you need to be careful with the linear constraint here. There are some subtleties. Okay, and so there's some like a very, just based on what I said today, there's a lot of immediate direction that you can pursue in the future. So for instance, I only consider the formula applied to the Schrödinger Bridge, but perhaps there are some other interesting applications that might interest you. Optimization problems with linear constraints. So the result here might be of interest to some of you. And also, because we have so the moment when you identify the constraint, so there's nothing to stop you from using just the entropic mirror descent, although I solely focus on that just because it's the most standard thing. But you can also consider some other types of dynamics for like optimizing Schrödinger Bridge or extending Schrödinger Bridge. Okay? So with that, I will conclude my talk, and I thank you for your attention.